Thank you for joining this session. My name is Chiu, and he's my teammate, Tim Ye.
I'm Tim Ye.
We come from Trend Micro Taiwan. We are all three researchers. So things start from the case, and it happened in December 2017, almost 2018. When I was checking the server, is server running, it is actually a Exchange server, and it is a front-end Exchange server, so which means it has an Outlook web app, and it is just an IIS server that connected to the mail service. So when I first touched this, I found this there is one suspicious thread which is running on the WINNTI.exe. So I'm very curious, so I dumped the process memory. And I found there is a memory block looks very strange. So this is the memory block. And you can see that it looks like an executable header, but without any MZ header. It has a P header, section tables, the structure is still complete, but there is no MZ, which looks it's more suspicious. And so I tried to recover the file when I was in the customer side. So how did I do? First I fix the MZ header, then I rebuild the PE, and I just throw the file into the IDEA Pro. Then I found two things strange. There's a string that looks like an URL, and the program called the HTTP ADD URL, and take this URL string as a parameter. So for the Webshell techniques, there's a website called MITRE ATT&CK. There's a bunch of different Webshell techniques used in the APT attack. So there's a one called the OWAAUTH. The font size might be small, but I already enlarged for you. It says it is installed as an IIS API filter on Exchange servers. So when I first touched this sample, I think it might be it should be an IIS API filter backdoor. But so is it really an IIS API filter backdoor? Actually, I'm very lucky. I got I got similar case before, so I have the IIS API filter registry path. For the IIS server to load the IIS API filters, you have to check the registry path. So I just connected back to the office, and I grab the registry path and mapping to the target machine, but there is nothing. So, which means this is not an IIS API filter DLL. So I keep looking into the malicious code, and I found that this sample responds to get or post command, and you can see that there is a very big while loop, and which means the program will continue to listen to get or post command. So later in the demo, you will see that. And let's take a deeper look. This program will respond to some strings after the request is decrypted, which means if you send the requested.html, this program will first decrypt it, like an RC4 or something. Then it will match to some strings. These strings are just like an OP code. What are these strings? These strings are CD, dir, copy, move, delete, or system info. And there is also a small piece of code that will do a create process, but the parameter is cmd.exe. So it looks really like a backdoor. So after we collect all the data from all Exchange servers, there are 3 Exchange front-end servers and a lot of Exchange backend servers, and we finally figure out how the program have been loaded. And by the way, in that unit, there are 3 front-end servers in customer side, and all the 3 front-end servers have this kind of backdoor. So this is the whole loading sequence. When the Windows boot up, the terminal service started, it will load a DLL called the sessenv.dll, the session environment DLL, which is a normal, which is a legal, it is a legitimate DLL. It will exist in all the Windows computer. And that DLL will load a non-existing DLL, which name is tsvip.srv.dll. And let's take a look at session environment DLL first. And this is just a small piece of code. You can see that there will load two different names. One is tsmsi.srv.dll, and another one is tsvip.srv.dll. So, which means if your computer have these two files or any of these, the session environment DLL will load it. But if you don't, that is fine because the terminal service will still running. Which means it's just like a third-party module or something that Microsoft should support. So what did hacker did? Hacker just changed the malicious loader DLL name to tsvip.srv.dll and put it under the System32 folder. And hacker tried to restart the terminal service. Then the whole backdoor will up and running. When the malicious DLL, the tsvip.srv.dll is executed, it will inject a small code into the WINNTI and then create a remote process. And that suspicious process will register the requested .html to IIS server. And when the IIS server got the requested .html request, then it will interact with the thread inside the WINNTI.exe. So, which is not the tsvip.srv.dll because this one already unloaded in the memory. So, it is very hard to find in this case because this case also use a lot of anti-forensic techniques. So let me point out something. For a Webshell, there is no script or no page file in your web folder, which means there is no requested .html, which means for a Webshell, it is an invisible Webshell. And the second thing is, the first one is, which means it is a fileless Webshell. And the second thing, the tsvip.srv.dll, it loaded only once. And it will unload it after injected to WINNTI, which means you can only find one suspicious thread. So there's no process, which means it's almost like a processless. And the third thing is, if you look at the IIS log and searching for the requested .html, there's nothing, which means this is logless. And the next is the tsvip.srv.dll is a big file. Actually, the file contents is small, but the malicious DLL is full of garbage code and junctions, something. And the file was locked to avoid some antivirus or some scanning tools at the user mode. So, which means because we are doing the live forensics, and which means this makes us very difficult to do a live forensics. And the last thing is the file timestamp have been changed. So when we think it is over, and a few months later, we saw an article. It's from SecureList. It's related to the Operation ShadowHammer. And there's a small, their researcher already announced some ShadowPath samples. And there are other victims. Which they said it will indirectly listen to TCP port 80 and look at the URL string, which is a requested.html, which is almost the same as our case. And the malware also responds to HTTP GET or POST. And it says which can help it remain invisible for a long time. So I think we believe that we are unless some similar samples, but we met it earlier. And we also think it is very hard to find. And that article also mentioned about the Operation ShadowHammer the source may come from a group name whose name is ShadowPad. And the other related samples keep coming in the mid of this year. I also got this sample, and this sample is not related to the first sample. And if you want to communicate with the backdoor, and you have to match the URL string, and you also have to match the cookie string. So that you can the version number will be 1.0 in here. And a few days later, we got version 1.5 here. The main change is that the cookie string has changed, but the biggest change is that the URL string is passed from parameters, which means you cannot make a simple pattern scanning on the network side, because hacker can easily modify this very easy. So similar samples keep coming in maybe I think it's around last month. We got almost the same backdoor as the first case, but it's different technique of DL hijacking. And for the reference, the MITRE also have the DL hijacking, but it's called the DL search order hijacking. By the way, in this case, hacker used the DL name, which is WLBSCTRL.dl, and it will also launched by the IKE-EXT service. So I think we need a solution. So in order to have these solutions, we have to trace in details. So let me introduce my teammate, Tin Ye.
Okay, thanks, Dolph. I'm Tin Ye, and and since that we think this kind of backdoor is hard to trace, it's very hard to find it. So we need some solution or some tool when we're doing the live forensics. So we need to know it more. First, we try to look up the Microsoft document, and we see the HTTP.ATT URL. This kind of function needs at least 2 parameters. One is request queue handle, which is a HTTP API handle, and the other is full qualified URL, which is just like the example HTTP plus AT port and a.html for this kind of example. And something is worth to say is that this HTTP API, this HTTP URL is not only existed in IIS web server, but also in every kind of Windows version from XP, SP2 and 2003. After this kind of version, Windows built in the HTTP SYS. So hacker can use this HTTP API to create their invisible web shell. But if the IIS server is installed in the Windows, the benefit of the hacker is that their program, their invisible web shell can reuse the port 80 or 443, so it can let the backdoor is hard to trace and bypass some firewall or some network traffic monitor. We try to download some sample code from the Microsoft document or GitHub. We download a HTTP server sample application to write the POC code. And in the box is our POC code about the web shell. We registered 443 port help.htm, and we can see that if we use some Microsoft live forensic tools, we can see the port 443, but the process is not the malicious process, it's a system, and the PID is 4. And it is because the API registered a URL and interact with the http.sys in the kernel mode, so it is hard to trace the process directly. And we can see if we use Process Explorer, we can see the malicious process server x86, but we cannot see any TCP/IP, any network traffic because it is in the kernel. And something need to discuss is the privilege. HTTP URL by default need administrator privilege. But there are some way to bypass the administrator privilege. Here we can use some built-in Microsoft tools, NetShell, to list all the URL access control list. And in the red box, we can see there is a reserved URL. AT port, temporary listen address, and the privilege is open to everyone. So hacker can use this reserved URL to register its malicious URL. So here is our POC. First, we try to register 443, 8080, and the 34567, this kind of port, but it is user privilege, so it will fail. But if we registered 80 port temporary listen address, the backdoor, invisible backdoor successfully registered in user privilege. And now we want to know how to detect it or how to find when we're doing the live forensics. There is a tool, built-in tool in Microsoft, NetShell. And NetShell also can print out some registered URL. But we think there are some efficient by just using the NetShell. At first, we think it is easy to bypass. Because NetShell rely on the registry, you can just hook or delete the registry key. NetShell NS HTTP, this registry key, delete it or change the DLL name. Then we can find in the box that it will show command was not found. It can bypass its check. And if we want to develop some EDR products, just use the NetShell is very hard to integrate with our product. And the last one is because we think that develop our self-developed IR tool is cool. Okay, and after a time to figure out which kind of API can we use, we find an API HTTP control service, which can display the PID and the registered URL. The return will show this kind of information. But when we use the API, we find that there are so many undocumented things. Like this one, PHTTP MGMT root info. What it is no document, and we cannot find anywhere. So we use the reverse engineering technique, try to find out. And finally, it is a pointer of integer one. And last, HTTP control service list function return value is output buffer, but the output buffer structure is also undocumented. So we need to trace by reverse engineering, and roughly speaking, it is a double linked list and will contain the PID and the registered URL. So we try to reconstruct the structure in the left side, and here are our invisible Webshell query tool. And we can see that in the middle red box is our POC backdoor, which can execute the dir command. And the upper is our invisible query Webshell tool. And we can display the pair of the PID and the registered URL. So we will give a small video demo and to try to introduce the, we use our invisible Webshell query tool and other Trendmicro live forensic tools to find this kind of malicious APT backdoor in the IR cases. Okay, first, we use a process scan to scan the malicious thread or malicious process. And we found a PID 412, WINNIT.exe. It may contain some suspicious thread. Take a little time. Okay, and next, we try to dump the memory of the PID. And we can see there will have some malicious string in the PID of memory of PID. Here are some like requested HTML, this kind of malicious strings. And we use our invisible query tool, try to query the pairs of PID and the registered URL. And we can find the PID and the requested URL, .html. And we try to interact with the IIS server. In the web root, there are some files, but no requested .html. If we test existing file, it will return the success strings. But and we test the requested HTML, it will continue cycling, waiting for the backdoor command. And if we test a non-existent URL, it will return 404 not found. And then we can check the IIS log. We can see the log contains some test URL like test and non-existent, but there is no requested URL. It means this kind of web shell invisible in the log. And finally, we use our tool hijack scan to scan if there is any DRL hijacking technique. And we found a tsvip.srv.dll in the system32 directory. Okay, that's it. Okay, let's make the conclusion. We introduce a new technique, and that is used in recent APT cases, which is very hidden and very hard to find it. And in our cases, this kind of technique or tactic is at least be used in 2 years, and based on compile time, it might be more than 5 years. It's very invisible. And talking to the target industry, we see the cases. They are targeting some high technology company or some government. And when talking to some possible threat actors, in our cases, we see that not only one threat actor use this kind of tactic, but the highest possibility actors are WINNTI or BlackTech, and they share the same origin. And last, we try to provide some method to catch up this kind of invisible web shell. And hopefully, we all can find and catch up them more easily in the following cases. And that's all our presentation. Thanks, everyone.
Thank you. Are there any questions from the audience? None? Then we have a few questions that were on Slido. The top question is, what makes a suspicious threat suspicious?
You mean this one? In our tool, there are several rules, and one rule is it's very technical. If your thread original entry point is not belongs to any module, then it is suspicious. Yeah, that's the basic algorithm. Yeah.
Next question.
How did the backdoor hide himself in process? Oh, it injected to the WINNTI.exe. Yeah.
And unloaded.
And unloaded immediately.
Malicious.
Yeah, because WINNTI.exe is a legal Windows process. Yep. Is it? How does you can imagine that there is a very big black how to say it? Known bad DLLs. It's just a data list. Yeah, but it is more complicated. It has its own algorithms. Yeah, it will. Yeah, it's very complicated. Sorry.
At scale.
Sorry, I don't understand. How can the technique be used to detect at scale?
At scale, if we can apply some EDR tools and in our the same method, if we can apply in our EDR tools, EDR can periodically scan this kind of malicious URL and check the certificate if it is good or not. Maybe it's kind of method.
Yeah, I think EDR solution might be better than our tool, but our tool is an IR tool, which is there will be no EDR software installed on the unit on the customer side. So that's the benefit.
Did any more questions arise from the audience itself?
As you said, it's injected himself in another process, but sometime even on Task Manager, if you open it, it's gonna see what process are under that process, and it's really obvious that's gonna show the process. But how they hide it, so it's not gonna show up even in those processes.
What?
I mean, when, for example, if you look at process, it's gonna already get injected. It's gonna show up what are sub-processes in that process.
Sorry, I don't understand.
I want to try to say if it's got injected to another process.
Maybe we can talk later.
The process.
Yeah, because there's other session, right?
Yeah. But it's a good question. Well, then I'll thank you very much. Sorry, Dov Chiu and Tim Ye.
Thank you.
Please give them another big applause.